This will be a quick video to answer a common but simple and important question. Basically, it's about setting up cases. Say you wanted to show someone what the soon case looks like. For those of you who don't know, soon is one of the 57 OLLs that you have to learn in the Friedrich method. Now, it is also sometimes referred to as the fish pattern case. I'm not sure why. This apparently looks like a fish to some people. So your goal is basically to get Rubik's cube to this state. A state in which if you apply the soon algorithm, the cube will be solved. So this is the soon algorithm. Okay, so one simple way to do this is to simply reverse the soon algorithm. This is not always a quick and viable option in practice, because you usually need a pencil and paper or something. But here's how you do it. Basically, you take any algorithm, so for example we have the soon. Now to get the inverse of this algorithm, you have to read it backwards, and you have to negate everything. Meaning that the clockwise terms become counterclockwise, and the counterclockwise become clockwise. So the result in this case would be R, U2, R prime, U prime, R, U prime, R prime. So this simply undoes soon. So if I apply that inverse, R, U2, R prime, U prime, R, U prime, R prime, then you can see that basically if I now apply the soon, I would be undoing all of the moves that I just made, and I would be solving the cube. So if I apply the soon now, then obviously I'm just undoing all of the moves that I did to screw up the cube, and I would be solving the cube. I would be returning back to the state I was in before. Now the second method is much more practical, but may take a little longer. Here's what you need to realize to understand how it works. So take the Rubik's cube in any state, for example the solved one, because it is easy to identify. Now if you take any algorithm and you apply it repeatedly, potentially many times, the cube will eventually cycle back to the solved state. This is simply a consequence of the fact that the cube has finitely many possible configurations. If you applied an algorithm and always got something new, then you could in theory generate infinite number of states. So anyway, the number of times you have to apply an algorithm to cycle back to what you started with is called the degree of that algorithm. So let's count what the degree of soon is. I will now apply the soon algorithm starting from the solved state, and we will count how many times it takes us to get back. So I'm applying soon. 1, 2, 3, 4, 5, 6. So we say that the degree of soon is 6. So here's a picture of the whole situation. We have the solved cube on the left. Now applications of soon algorithm are green arrows, and applications of its inverse are magenta arrows. Our task was to set up the soon algorithm, which in a diagram lies on the bottom, one position counterclockwise from the solved state. I already showed you the easy way of getting there, and that is through the inverse. That's the magenta arrow that leads to it right away. But now you can see that the second way of getting there is to follow the cycle along green arrows, and after 5 applications of the soon, you will get to the actual soon case. And this is true in general, not just for the soon, but for any algorithm. To set up a case that is solved by some algorithm x, you have two options. You either apply the inverse of the algorithm, x prime, to the solved cube, or apply x itself many times until you get to the position just before the solved state. Now this may take a while because some algorithms can have high degrees. I think the most I ever encountered in practice was like 18 though, and that is rare. The good news is that a big majority of algorithms have very low degrees, like 2, 3, 4, or 6. For example, all of the PLLs have degrees 2 or 3, so those are always very easy to set up. And I will show some examples now. Okay, so examples. Let's say you wanted to set up this OLL case, called the chameleon. But all you know is how to solve the chameleon, and the algorithm that solves it is the X that I was talking about. So we have two options. We can write out the solution on paper, which in itself is often quite hard because you remember it from your muscle memory, not the string of symbols. And then once you have it written out, you invert it, and then you apply it to a solved cube. So I went ahead and I did that just to show you that it works, and it's FR prime, F prime, R, U prime, R prime. And of course you get that. Alternatively, just start with a solved cube and apply the solution to the chameleon on it over and over until you get to it. So we're traveling along the cycle now in the other direction. So I applied it once, we're not there yet, applied it again, and there we are. So we were lucky this time because the degree of the chameleon, that algorithm, is only 3. So I only had to apply this twice. Lastly, I want you to realize that you can also set up F2L cases. For example, this case here, this corner, this edge. To set this case up, what you could do is you could write out the solution on the paper and then invert it. So that's what I did, and I came up with R, U, R prime, U to R, U, R prime. So that is the case. Or the other way, of course, is that you just apply blindly that case. You pretend that you have it, and you apply it to the solved cube, and until you get it, actually. So I'm pretending that I have this case, and I'm just solving it. So I'm not there yet. So I'll solve it again. Okay, I'll do it again. Not there yet, so I'll pretend it again, and there we are. That's the F2L case. And that's how you set up any case that you like, be it for F2L, OL, PLL, or even cases for any other method, not just the Friedrich method. I'll see you guys later.